Hi all, welcome to Engineers Think Box. This is Sharu. So in this video we'll discuss problem on product quantization error, which is also called as product round of noise power. So before getting into the problem, I would like to recall the steps involved in solving this problem. So first thing is from the given question we will be taking this transfer function and we will be representing that transfer function either in direct form or in the cascade form. We all know direct form consists of two types, that is direct form 1 realization and direct form 2 realization. So as far as this product quantization error is concerned, we will be going with direct form 2 where the transfer function will contain numerator and denominator. This numerator part is there, right? Numerator's coefficients will go first thing is this structure will consist of input, that is x of n, and y of n, that is output. The numerator coefficients will go on the right hand side of the system, that is structure, and all the arrow marks will be this side, that is from left to right. So as you could see, the first coefficient is b0, and the second coefficient is b1. The second coefficient is b1, which is placed here into z inverse, and the third coefficient is b2, z power minus 2. So the next coefficient is b2, and when these two coefficients are added, z power minus 2 will be there. And coming to the denominator part, this denominator part will be placed on the left hand side of the structure, and the arrow marks will be from right to left. So now the coefficients will go like this. This one will be placed here. This minus a1 will be placed here. That is one more thing which you have to remember is for this direct form 2, the numerator part will be positive. The numerator thing will be in positive, will be addition terms, and the denominator will be in negative terms. This is the general structure of the direct form. Okay, so when we are going to compare it with the general structure of the direct form, this is in minus a1, right? So minus a1 a1 will come here as such, but as I said, for denominator minus should be there in the denominator, but here it is plus a2. So what we will do is we will be putting it as minus of minus a2. So we will be representing it in the minus form, so minus a2, and the direction will be from right to left. And we will also have e1 of n, e2 of n, e3 of n, and e4 of n. These are the errors formed due to this realizations. The next thing is cascade. Coming to this cascade form, here we will be, in the question we will be having two transfer functions, h1 of z and h2 of z. We will be representing h of z here as h1 of z multiplied by h2 of z. Okay, so now as usual, in order to represent it in the cascade form, the input will be x of n, the output will be y of n, and this part is given in the left hand side, and this part is described in the right hand side, and two errors are formed, that is e1 of n and e2 of n. So this is how the first thing, after taking the transfer function from the question, either you will be realizing it in the direct form or in the cascade form based on the question. If it is if only one transfer function is given, we will be representing in direct form 2. If there are two transfer functions given, we will be representing in the cascade form. This is the first and foremost step. Next, what we will be doing is, again, for direct form 2, what we will be following this formula. Sigma epsilon square is equal to n sigma e square divided by 2 pi j closed counter integral of h of z inverse into z inverse dz. This n will represent the total number of noise factors present in this thing. So here you could see 4 noise factors are present. So for this case, n value will be 4. That is E1 of n, E2 of n, E3 of n, and E4 of n. Coming to the cascade form, what we will be doing is, as we all know, we will be having two transfer functions for cascade, h1 of z and h2 of z. If the question is given in the cascade form, first thing what we will be doing is, we will be calculating sigma epsilon 1 square. The formula for this is sigma e square by 2 pi j closed contour integral of h of z inverse into z inverse dz. Next thing what we will be doing is, we will be calculating sigma epsilon 2 square, where the formula will be sigma e square by 2 pi j closed contour integral of h2 of z inverse into dz. And finally, in order to get this sigma epsilon square, we will be adding this both. So this is about the direct form 2 and cascade form 2. So based on the questions, we will be solving the problem. So now let's get into the problem. So now the question is, consider the transfer function h of z that is represented as h1 of z and h2 of z multiplied by h2 of z, and the h1 of z is 1 by 1 minus a1 z inverse, and h2 of z is 1 by 1 minus a2 z inverse. Now what they have asked is, find the output round off noise power, and we have to assume a1 value of 0.5 and a2 value as 0.6. So first thing is, we will be realizing it in the cascade form since there are two transfer functions. So what we will be doing here is, this thing h1 of z will go on the left hand side, and this h2 of z will go in the right hand side, and this x of n and will be the input, and this y of n will be the output, and E1 of n will be error factor, E2 of n will also be another error factor. So now for cascade form, what we will be doing is, we will be following this two formulas method. So first thing what we will be calculating is sigma epsilon 1 square, for which the formula is sigma e square divided by 2 pi j closed contour integral of h of z inverse into dz. So we know the h of z is given in the question is h1 of z into h2 of z. So in the place of this h of z, I will be putting h1 of z into h2 of z, and in the place of h of z inverse, I will be putting h1 of z inverse into h2 of z inverse. And before substituting the value of h1 of z and h2 of z, I will be making some small modifications in that. What is this is, in the question it is given as a1 value as 0.5, right? So I will be substituting this 0.5 value in the place of a1, and this z inverse will come to the denominator. Similarly, a2 value is given as 0.6. So 1 minus 0.6, this z inverse will come to the denominator. After taking LCM, it will be like this. Now what will happen is, this z will go to the numerator. If you are going to represent this 1 by 1 divided by 6, how you will be representing it? You will be representing it as 6. This 6 will go to the numerator. Similarly, this z will go to the numerator, and h1 of z can be rewritten as like this, z by z minus 0.5. Similarly, after taking LCM, this z will also go to the numerator, and h2 of z will be z by z minus 0.6. So now, if you're going to substitute it in this formula, what will happen is, sigma e square 2 pi j will remain here as such. H1 of z is, it will be like this. Just a minute. Okay, h1 of z will be z by z minus 0.5. h2 of z will be z by z minus 0.6. H1 of z inverse will be, in the place of z, we will be putting z inverse, that's it. So z inverse divided by z inverse minus 0.5, z inverse divided by z inverse minus 0.6 into this z inverse. So now what will happen is, this z and this z inverse will get cancelled, this z and this z inverse will get cancelled, and remaining only this z inverse will remain. So that is what is written here. This one Z inverse alone will remain. And coming to the numerator part, Z minus 0.5, that is Z minus 0.5, Z minus 0.6, Z inverse minus 0.5, Z inverse minus 0.6. Okay, now in order to solve it, we will be calculating the residue. That is, just a minute. In this thing, one thing which you have to notice, this stuff is there, right? This part of the formula. This part of the formula is residue. That is 1 by 2 pi j closed counter integral of Z inverse by this whole thing. To make it clear, I'll mark it in this formula. This whole formula is residues formula. So what you will be doing is 1 by 2 pi j closed counter integral h of z inverse into dz. This formula is residue formula. So first I will be calculating the residue for this equation. So in order to calculate the residue for this equation, I will be calculating the poles. Poles means whenever the denominator is equated to 0, those are called as poles, and whenever the numerators are equated to 0, those are called as zeros. So here we are having 4 denominators, right? That is 4 factors in the denominators, right? So z minus 0.5 is equal to 0, so z is equal to 0.5. This is one pole. Z minus 0.6 equal to 0 now. Z is equal to 0.6 is one more pole. Z inverse minus 0.5 is equal to 0 now. Z value will be 1 by 0.5. 1 by 0.5 value is Z is equal to 2. This is one more pole. And if you are going to equate this Z inverse minus 0.6 equal to 0 now, the Z value will be 1.667. Now, when you are going to plot this in the unit circle will range from 0 to 1. Only this 0.5 and 0.6 will lie inside the unit circle. This 1.6 and 2 will lie outside the unit circle. The Z values that are present inside the unit circle are considered to be stable, and it will contribute to the system. These two things are considered to be unstable, and they will not contribute to the system. So what will happen is these two stuffs will be omitted, and only these two poles, that is Z is equal to 0.5 and Z is equal to 0.6. These two poles alone will be considered. So now for this thing, for this 1 by z minus 0.5, 1 by z minus 0.6, 1 by z inverse minus 0.5, 1 by z inverse minus 0.6 into z inverse, for which we will be having two poles, z is equal to 0.5 and z is equal to 0.6. Now what we will be doing is, we will be substituting z is equal to 0.5 here. That is, we will be calculating the residue at z is equal to 0.5. What we will be doing is, at which point we are calculating residue, if it is there, right? That equation should be placed above it. Say to make it clear, I'll explain it properly. So now we have taken z is equal to 0.5, for which we will be calculating the residue, right? This is z minus 0.5. For this equation only, you got 0.5 as the pole, for which the respective numerator will be placed as z minus 0.5. That is, our ultimate aim is to cancel that thing. If z is equal to 0.5 is the residue, our ultimate aim is to cancel that whole stuff from the thing. So what we will be doing is, we will be placing z minus 0.5 as the numerator, so this both will get cancelled. And after this, in the next step, what we will be doing is, we will be placing, wherever z is there, we will be placing 0.5. So 1 by 0.5 minus 0.6, 1 by z inverse will be like 1 by 0.5. So that is what is mentioned here, and here it is again 1 by 0.5. So whichever residue we are going to take, that respective factor which should be cancelled off. So in order to make it, I will be putting it in the numerator. So now if I'm going to put it and if I'm going to calculate a normal math, I'll be ending up with this value minus 9.524. Similarly, for z is equal to 0.6, we'll be calculating residue. Now we have to cancel that factor. So I'll be putting the numerator in this place so that this both will get cancelled. Now again, wherever z is there, I'll be putting 0.6, z inverse, so 1 by 0.6, z inverse 1 by 0.6, so z inverse and again 1 by 0.6, so now it will be 13.39. So now to order to calculate the total residue, I will be adding this both stuffs. So 13.39 plus minus 9.524 is 3.87. So now the thing is, for this entire stuff, we have got the answer as 3.81. Sorry, 3.87. With this, you have to multiply this thing, sigma e square. So 3.87 multiplied by sigma e square is the that is the first thing, sigma epsilon 1 square. Similarly, we will be calculating for epsilon 2 square. That is the step here. Okay, so epsilon 2 square we will be calculating, where we will be considering only h2 of z in this case. So now let's do that. So this is the formula for calculating sigma epsilon 2 of z. So what we will be doing is h2 of z. h2 of z is from the question we have taken it as z by z minus 0.6. So h2 of z, first thing is z by z minus 0.6. h2 of z inverse. So z inverse by z inverse minus 0.6 into z inverse into dz. Now again we will be calculating the poles to obtain the residues. So here there are two factors in the denominator. We will be equating it to the 0. So the first pole will be z is equal to 0.6 and the second pole will be z is equal to 1.6. So obviously this 0.6 will lie inside the unit circle. So I will be considering only this as poles and I will be omitting this. So now here, so if z is equal to 0.6 now, I will have to cancel this part. So in order to cancel this part, I will be putting it in the numerator part also, that is irrespective factor, and after cancelling this, only this will remain. So 1 by this z inverse is 1 by 0.6 minus 0.6, then this z inverse is 1 by 0.6. If you're going to calculate, if you're going to solve it, you will get 1.5625. Again, we have calculated only this part. This is the residue formula. So 1.5625 multiplied by this thing. So that is what is did here. So now finally what we will be doing is, as per this, we will be adding this both. So that is what is the next step. We will be adding this both. So the first thing is this thing, sigma e square into 3.87. That is the first thing. And this is the second thing. I have put it here. So if I'm going to add both, I will be ending up with this value. We know that sigma e square can be written as q by 12. Q value is 2 power minus 2b by 12. So so what I will be doing is, in this place I will be substituting this value, 2 power minus 2b divided by 12 into 5.43. Now this 5.43 divided by 12 is 0.4527. This 2 power 2 minus 2b, 2 power minus 2b will come here as such. So this is the final answer, sigma epsilon square. So for cascade thing, what you will have to do is, you will be calculating sigma epsilon 1 square, sigma epsilon 2 square, and you will be adding the both. This is all about the product quantization error. Thank you.